Our last coordinate system is spherical coordinates, and it differs from cylindrical coordinates in that all distances are now measured primarily from the origin. It is something that focuses on the origin, and we now have, instead of a radius, a height, and an angle, we now have a radius and two angles. So this is best illustrated in the schematic that we have drawn here. So for any given point in space, given by this red dot, the coordinate rho is the distance from the origin. This is not to be confused with the old cylindrical coordinate r, which is sketched there in a lighter pencil in green. R was the distance from the z-axis. So that would be up at this point that we have in question. That would be this distance would be r. Instead, rho is the distance from the origin, and we can see that those are different, and that's why it's given a different name. Then we have two angles associated with this coordinate system. The first angle, phi, is also new, and it is called the polar angle. It is the angle away from the z-axis. So the reason it's called the polar angle, if we imagine the Earth living on this coordinate system with its center at the origin, then the z-axis would be the North Pole, and the polar angle would be the angle relative to the North Pole. This is not latitude. Latitude is an angle measured relative to the equator. This is not latitude. It's different than latitude. It would be basically 90 minus latitude, essentially. So it is 0 at the North Pole. It increases to pi over 2 at the equator, and it increases down to pi at the South Pole, and it does not exceed pi. Finally, we have theta, which here is called the azimuthal angle, and it is the angle relative to the x-axis of the projection of our point down into the xy plane, just like it was in cylindrical coordinates. So theta remains the same as cylindrical coordinates, but rho and phi are new. It's good to just review the possible bounds on these variables. So as in cylindrical coordinates, rho is always reckoned as a positive distance from the origin. You can interpret a negative value of rho, but if you're asked to identify the coordinates in spherical coordinates of some point, we always choose the positive value of rho, distance from the origin. Phi, as we just stated, starts at 0 and increases and reaches pi, or 180 at the South Pole. It doesn't make any sense to extend it beyond that, and so we let phi go only to pi. Finally, theta, as in cylindrical, wraps around the xy plane and goes from 0 to 2 pi. So these are the bounds on our new spherical variables, rho, phi, and theta. The equations for relating spherical coordinates to Cartesian coordinates can be obtained by means of cylindrical coordinates, which we're already familiar. So if we look at this image here, we have this rho and this angle phi, and rho and r and z here make a right triangle. Here, here, and here. And let's look at that right triangle a little more carefully down below. So here it is again, our right triangle rho. This would be the height z in the old cylindrical and the radius r in the old cylindrical coordinate system. And we can see that rho and phi are related to r and z. Specifically, if this angle here, the polar angle, is phi, then so is the top angle of this triangle here by basic geometry. And if this is the hypotenuse of a right triangle, and here's an angle phi, then we can relate r and z. R is going to be rho sine phi, that would be this edge, the opposite edge to phi will be rho sine phi, and z will be rho cosine phi, the adjacent edge here. And so if the old cylindrical coordinates r and z can be determined from rho and phi, then because we can determine the Cartesian coordinates from the cylindrical coordinates, we can just take these expressions for r and z and stick them into our cylindrical expression. So x becomes r cosine theta, or rho sine phi cosine theta. Y becomes r sine theta, or rho sine phi sine theta. And z, which was just z before, now becomes rho cosine theta. So it's clear that these expressions are the same as the cylindrical coordinate expressions if we use these expressions for r and z, and so these are then the correct expressions in spherical coordinates of the spherical coordinates for the Cartesian coordinates. And similarly, if we want to obtain inverse relationships, if we want x, y, and z in terms of rho, phi, and theta, we can use the inverse relationships from cylindrical coordinates to help us out. We have these right here, allowing us to say that rho equals r squared plus z squared, and phi by this diagram is the arctangent of r over z. And then if we know rho and phi in terms of r and z, well, we also knew r in terms of x and y, and so that allows us to get rho as r squared, or x squared plus y squared plus z squared. Phi is the arctangent of r here, x squared plus y squared to the 1/2 over z, and theta, as before, was the arctangent of y over x. So these are our inverse relationships that allow us to get from from Cartesian to spherical. These are the equations for spherical to Cartesian. That's kind of a lot of information, so it's fine to pause and review until looking at the diagrams, kind of let that soak in. So if we want to do integrals in spherical coordinates, we are, of course, going to have to calculate dv. And that, as usual, as in the general sense, is going to require us to take partial derivatives of the position vector with respect to rho, phi, and theta. So our position vector x, y, z is given right here by these expressions, and we now just take derivatives with respect first to rho, and then phi, and then theta, and we get 3 tangent vectors. The rho derivative is sine phi cosine theta, sine phi sine theta cosine theta. The phi derivative, we get rho cosine phi cosine theta, rho cosine phi sine theta, and negative rho sine phi. And the theta derivative, negative rho sine phi sine theta, rho sine phi cosine theta, and 0, since there's no theta dependence in the z coordinate. We then need to take the magnitude of the scalar triple product, which is the determinant of this 3×3 matrix. If we just draw lines here and make it a matrix and take the determinant, we can do so, and it gets kind of messy. There's lots of terms. There are 4 terms, it looks like. We get nothing from this diagonal, but then we get a sine phi sine theta times negative rho sine phi times negative rho sine phi sine theta. And that gives us this term right here. And then we take the next diagonal, cosine phi, rho, cosine phi, cosine theta, rho, sine phi, cosine theta, and that gives us a term here. Similarly, we have 2 upward diagonals in that determinant, which give us 2 more terms. Okay, it's a little bit messy, but if we work this out, we'll see that we have some common factors. Every single one of these terms has a rho squared sine phi in it. Rho squared sine cubed phi, rho squared sine phi, rho squared sine phi, rho squared sine cubed phi. So we'll pull that out. That leaves us with 4 a little bit simpler terms, all involving squares of the sines and cosines of phi and theta. And we'll see that we pick up sine squared phi plus cosine squared phi times sine squared theta. That's going to give us just a sine squared theta. And we have a sine squared phi plus cosine squared phi cosine squared theta, which is going to give us a cosine squared theta. And lo and behold, that's just 1. And so this whole bracketed expression is just 1. We get for the determinant of that matrix just rho squared sine phi. And so the volume element finally is rho squared sine phi d rho d phi d theta. A picture helps illustrate this a little bit. If we take these 3 direction vectors, rho phi, r rho, r phi, and r theta, and take just the magnitudes of these 3 things, the first is delta rho. The magnitude of r rho delta rho is just delta rho. The magnitude of rho phi is rho, and the magnitude of rho theta is rho sine phi. And so if we imagine now small increments, delta rho, delta phi, and delta theta, we get some, I guess our book calls it a spherical wedge, with sides delta rho, rho delta phi, and rho sine phi delta theta. And in the limit, as these increments become small, this starts to look more and more like a cube, whose volume does indeed look like rho squared sine phi. That's because this coordinate system is what's called an orthonormal coordinate system. that all the directions are orthogonal to one another. However, our formula of taking partial derivatives and their determinant, while it obscures this geometrical relationship, does work even when the coordinate system is not orthogonal. So these pictures are worthwhile. I didn't really focus on them until the end because the math always gives you the right answer regardless of whether or not you can draw the pictures. And so simply by taking that determinant, we get the right magnitude of the scalar triple product. So that's rather a lot of just calculating things, a lot of algebra. Just focus on the fact that we have this picture of spherical coordinates, how they're defined. That definition leads to the three partial derivatives, leads to the scalar triple product, which leads to the volume element. So it's a lot of steps, but ultimately at the end of the day, this is the object that we need to do integrals. So for example, the simplest possible integral in spherical coordinates, compute the volume of a sphere. We know the answer, so we'll be able to check and make sure that we're right. The volume integral of a sphere to find the volume will just be the volume integral of 1 dv. And all that we really need to do is determine the correct bounds within spherical coordinates. And so the simplest possible object is a good place to start. It's a sphere of radius r that is all points less than or equal to a distance capital R from the origin. Well, that distance from the origin is encapsulated in the coordinate rho. So rho is going to go from 0 to capital R. Phi is not specified. Phi can be any of its valid angles, which are 0 to pi. As is also true with theta, theta can be anything between 0 and 2 pi. So we're not talking about slices of a sphere. For instance, if we had talked about the upper half of a sphere, we would have let phi go from 0 to pi over 2. If we had talked about that part of the sphere with positive values of, say, y, then theta would have gone from 0 to pi. Positive values of x, theta might have gone from minus pi over 2 to pi over 2. And so on. But this is the whole sphere, and so we have all values of phi and all values of theta. So that's all we need to set up our triple integral. Our dv becomes rho squared sine phi, d rho d phi d theta, and so our bounds on our integrals working inside to out are 0 to r, 0 to pi, and 0 to 2 pi. Now this integrand is a product of a function of rho and a function of phi, and these are constant bounds on these three integrals, and so because of those two facts, we can break this up into a product of three separate integrals. The integral from 0 to 2 pi of d theta times the integral from 0 to pi of sine phi d phi times the integral from 0 to r of rho squared d rho. And these are, of course, very simple. We get theta from 0 to 2 pi, negative cosine phi from 0 to pi, and 1/3 r cubed. Sorry, that should have been rho cubed from 0 to capital R. This is, of course, 2 pi. Negative cosine of pi is 1 minus the negative cosine of 0 is, again, 1. So this gives us a 2 for 4 pi, and this is just a third, so we get 4/3 pi r cubed, as we know the answer to be. Another example. This looks like it won't be so bad. It actually involves a fair amount of computation, so it's not a bad example. Give us some confidence working with spherical coordinates. So compute the volume integral. Now we're not computing a volume by itself, but a volume integral of some kind of density, something with units of something per square, per cubic length, something per volume, over a volume, where the volume is now part of a sphere, the interior of the unit sphere above the cone z equals the square root of x squared plus y squared. So, again, 3 steps. We have to parameterize the volume, convert the integrand, and then we already know what dv equals in spherical coordinates for volume integrals. So to parameterize, we draw a picture. Here's the top of our unit sphere. Here's the cone. Z equals basically r. And so what we have here is some thing that looks kind of like a snow cone. What are the proper bounds on the parameters for this kind of object? Well, first of all, it looks clear that theta goes from 0 to 2 pi, so we'll do that. This is the unit sphere, so all values within this sphere lie between 0 and 1 in rho, so that's pretty straightforward. But what about phi? We need to know this angle right here. This is the polar angle, and it goes from the z-axis to the line z equals r. Well, that is just a line with a 45-degree angle on both sides. So this angle right here is pi over 4, and so phi goes from 0 to pi over 4. And this parameterization encompasses every bit of this, the interior of the snow cone, and nothing more. We need to change the integrand. 1 plus x. X becomes, in spherical coordinates, rho sine phi cosine theta. So the integrand becomes 1 plus rho sine phi cosine theta. And the volume element, dv, we've already calculated, rho squared sine phi d rho d phi d theta. So now we put it all together, and we've got a little bit of algebra and integration to do. The volume integral of 1 plus x dv becomes the triple integral over these bounds of 1 plus rho sine phi cosine theta times rho squared sine phi d rho d phi d theta. After we write this down, however, naturally this piece is the integrand and this is dv, but after we write it down and we start thinking about it as a triple integral, this all becomes the integrand, and these are our variables, the order in which we integrate. So rho first, this is going to be when I distribute through rho squared sine phi plus rho cubed sine squared phi cosine theta. When I integrate, I get 1/3 rho cubed sine phi plus 1/4 rho to the 4th sine squared phi cosine theta. Fortunately, the bounds on rho are simple, and we get no contribution at 0, only at rho equals 1, which replaces all my rho's to a power with just 1, which gives me this expression. So I've substituted 1 for my rho's, and I've taken my sine squared theta and replaced it with 1/2 times 1 minus cosine of 2 theta. That half angle identity is what will allow us to integrate that function of phi, which is our next step. We integrate in phi. The integral of sine phi is negative cosine. The integral of 1 minus cosine 2 phi is phi minus a half sine 2 phi. Cosine theta, again, treated as a constant since we haven't yet integrated over theta. Plug in pi over 4. Cosine of pi over 4 is negative root 2 over 2. Pulling this negative sign inside. Cosine of 0 is going to be minus the cosine of 0. Minus negative cosine of 0 is just 1. So I have here negative root 2 over 2 plus 1, all times a third. Here, theta gives me pi over 4. That gives me pi over 32. Sine of 2 pi over 4, that's the sine of pi over 2, which is 1. So that becomes minus 16 cosine theta. Almost done, just have to integrate in theta. This is some constant. Integrating it gives us theta. Integral of cosine theta is sine theta. Sine of 0 is 0, sine of 2 pi is 0, so we get nothing from this term, and all we do is multiply this term by 2 pi. So we get an answer. And this gives you sort of a flavor of how integrals in spherical coordinates work. Lots of sines and cosines, lots of half angle, double angle identities that need to be recalled and have you need to have them available at your fingertips because that's the tools that you need to do the integrals that result.